Hello friends, in this video I will discuss the photoelectric effect and Compton effect, and both of these effects demonstrate the particle nature of electromagnetic waves. So first we will discuss the photoelectric effect. So what is photoelectric effect? It is the ejection of electrons from a metal surface when light is incident on it, and the metal is known as photosensitive material, and the ejected electrons are known as photoelectrons. And here we can see, if we have a metal plate and the electromagnetic radiation falls on it, then the electrons are ejected, and these are known as photoelectrons. And this effect was discovered by Hertz in 1887, and he used the ultraviolet radiation, and when it strikes a metal surface, the electrons are ejected from the metal surface. So there are certain conditions for photoelectric effect, that photoelectrons are emitted only when the energy of the incident radiation h nu is greater than phi, or the work function, where phi is work function and h is Planck's constant, nu is the frequency of radiation, incident radiation. Number of photoelectrons emitted per second is directly proportional to intensity of incident radiation. And the maximum energy of photoelectrons, it does not depend on the intensity of incident light, but it depends only on the frequency of the incident light. In this slide we will discuss the Einstein's photoelectric equation, which was given by Einstein to explain the photoelectric effect, because some of the phenomena were not explained at that time. And if the incident photon have energy h nu and metal have the work function phi, and the kinetic energy of photoelectrons are half mb square. So the energy of a photon, incident photon, E equal to h into nu, or hc by lambda, and the work function of the metal is defined as phi equal to h into nu naught, where nu naught is known as the threshold frequency. And if we use the conservation of energy law, then energy of incident radiation should be equivalent to the work function plus kinetic energy of electrons, and incident energy is h into nu equal to h nu naught, that is the work function, plus the kinetic energy half mb square, or half mb square equal to h nu minus h nu naught. And the maximum kinetic energy, or the velocity, we cannot determine, so it is calculated experimentally using the stopping potential, or measurement of the stopping potential, which is denoted by V naught or Vs. So this kinetic energy half mb square equal to E into Vs, and this is equal to h nu minus h nu naught. So this equation is known as Einstein's photoelectric equation, and it explains that the kinetic energy of uh, liberated electrons does not depend on the intensity of the incident radiation. It depends only on energy or frequency of the incident photons. Experimentally, to understand the photoelectric effect, we need a vacuum chamber. One emitter or cathode is there, and anode or collector is here. And if we shine some light on this cathode, the electrons will flow towards the anode, and there will be some current in this circuit, which we can see using this emitter. So this current is known as photocurrent. So if we apply a negative potential, if we use this battery, and negative potential is used to collector and positive to emitter, then this negative collector or anode will repel the electrons from this plate, and at certain voltage, if we increase the voltage, there is no electron will reach to collector due to the repulsion, and this value of potential is known as the stopping potential, where we will see the zero current, means no electrons can go to collector. So there will be zero current, and this potential at which we will get the zero current, it is known as the stopping potential. And this stopping potential, the kinetic energy of electrons is related to the stopping potential as E into Bs, where E is the charge of electron and Bs the stopping potential or voltage. So this, from here we can measure the kinetic energy of these electrons. And here kinetic energy equal to, this is from Einstein's equation, h nu minus h nu naught, or h nu minus phi, that is phi is work function. So from here we can find out EBS equal to hc by lambda minus phi, and we can see that the kinetic energy depends only on nu or lambda of the light, means frequency or wavelength of the light, but not on the intensity of the source of light. And for this explanation, Einstein got the Nobel Prize for this explanation based on the basis of photons. And this Einstein's equations and explanation, it was verified by experimentally by Millikan by plotting this curve. If we have EBS equal to h nu minus nu naught, so BS will be h by E nu minus nu naught, and on x-axis we plot nu and y-axis BS, and Millikan plot it for different metals, suppose for aluminum, zinc, nickel, and he got the straight lines. And if we take the slope of these straight lines, it is h by E, so it is same for all materials. So from the plots Bs versus nu, the slope was h by E, and Millikan found that the value of h determined from these experiments, they are matching well with the values obtained from the other experiment. So it verified the Einstein's photoelectric equation also, and it means that photoelectric effect, it confirms the energy in the form of discrete quanta for the photons or the particle nature of photon. And the work function for some metals are shown in this table, and we can see greater the work function, we will need more energy to eject the electrons from the surface. So if we see cesium have 1.9, potassium 2.2, sodium 2.3, lithium, so these alkali metals have low work function, so these are best photometals to eject the electrons, whereas we can see that copper, silver or platinum, they have very high work function, so it is not easy to liberate the electrons from these metals. Now we will discuss briefly what are X-rays, because now we will move to the Compton effect, and in Compton effect X-rays were used instead of the visible light. So X-rays are electromagnetic waves and they are high energy photons, and the wavelength of X-rays are from 0.01 nanometer to 10 nanometer, means they have a low wavelength or high frequency. And when this electron, how we generate the X-rays, it is when high energy electrons, they strike with some target, and then we get some electromagnetic waves like X-rays, highly penetrating radiation. And X-rays are also diffracted as the light wave diffracts. So, and they also follow the Bragg's law of diffraction. And X-ray production is like inverse photoelectric effect, means in photoelectric effect we get the electrons when electromagnetic radiation is incident. Here electrons are incident and we are getting the electromagnetic wave, so it is known as inverse photoelectric effect, the generation of X-rays. So this is about the X-rays. Now we discuss the Compton effect. So it was an experiment done by Compton in 1922, which also confirmed the quantum theory of light and particle nature. And Compton effect, which is also known as Compton scattering, it is the increase in the wavelength of X-rays or any other electromagnetic radiation that have been scattered by the electrons. So this figure shows the interaction of incident radiation with an electron. suppose this is the incident radiation which have the wavelength lambda, and if it interact with electron, then this is scattered electromagnetic radiation or scattered X-ray which have the wavelength lambda prime and scattering angle is phi, and this incident energy is given to some of the energy will given to this electron and it moves, and this moving electron makes angle theta with this axis. So there is shift in the wavelength lambda dash minus lambda or lambda prime minus lambda equal to h by m naught into c 1 minus cos phi. So this shift is known as the Compton shift, and it does not depend on the lambda or wave frequency of the incident radiation. It just shift depends on angle, scattering angle phi only. This is the derivation. Here we see that incident photon interacts with the electron which was at rest initially, and the scattered photon goes in the direction at angle phi, and this scattered electron or recoiled electron is at angle theta. So we will use the energy conservation and momentum conservation laws, and then we will find the final result or final formula. So for the energy conservation we have used this first image, and second, because energy is scalar quantity and momentum is vector quantity, so we will have to take the component of the momentum vector because it is an angle phi and theta. So we will take, suppose this scattered photon have this incident was momentum h nu by c, and scattered have h nu prime by c in phi direction. So it will have the component, horizontal component is h nu prime by c cos phi, and the vertical component will be h nu prime by c sin phi. Similarly, this p, the momentum of electron, will also have some horizontal and vertical component. Horizontal will be p cos theta and vertical component will be p sin theta in opposite in this direction. So if we put see the energy conservation law, law of photon energy, should initial energy before the collision should be equivalent to final energy, that is after the collision. So initially incident photon have energy h nu plus it interacts with the electron at rest, so it will have only rest mass energy m naught c square equal to h nu prime plus, now this is moving electron, so its total energy will be mc square, that is moving mass, or we can write m minus m naught c square equal to h nu minus h nu prime, and m minus m naught c square, this is known as the kinetic energy. This mc square, the total energy, minus m naught c square, rest mass energy, that is kinetic energy, k equal to h nu minus h nu prime. So this is equation number 1. Now for the momentum conservation, initially electron was at rest, so its momentum was 0, and final it have some momentum p m into v. So the x component on x-axis we can see from that image. On x-axis the incident photon have momentum h nu by c plus 0. This is in x direction before collision, and on x direction the components, horizontal component, are h nu prime by c cos phi plus p cos theta. Similarly, on y-axis there was no movement, no momentum is there, so 0 in before collision. After collision we will have the vertical components of which include sin phi and sin theta. So h nu prime by c sin phi for the radiation, and for the electron it is p sin theta in opposite direction, so we take minus p sin theta. So these are the horizontal and vertical component of momentum, they should be conserved. And now we have to little bit rearrange these terms, equation number 2 and 3. H nu by c equal to h nu prime by c cos phi plus p cos theta, and it will give us pc cos theta equal to h nu minus h nu prime cos phi. If we take this c as LCM and then multiply pc cos theta equal to this. Similarly, P into C sine theta equal to h nu prime sine phi. And now if we square these two terms 4 and 5, because we need to get p square c square term, so if we take the square of 4 and 5, p square c square cos square theta plus p square c square sine square theta, if we add these terms, so right hand side also h nu minus h nu prime cos phi whole square plus h nu prime sine phi whole square. And if we open this square, then p square c square equal to, this will be cos square theta plus sin square theta equal to 1 equal to h nu square plus h nu prime square cos square plus 2 times h nu into h nu prime cos phi plus second term h square nu prime square sin square phi. And if we rearrange again, it will be p square c square equal to h nu square minus 2 h nu prime cos phi minus h nu prime whole square. And also we know a relation between total energy is equal to kinetic energy plus rest mass energy m naught c square. So E equal to this. And finally we got a relation p square c square equal to k square, yeah, or k kinetic energy square plus 2 m naught c square into ke. So now this equation number 9 we can find out, also we can compare it with equation number 6, but we have to replace this kinetic energy term with h nu minus h nu prime, because we need the relation in nu or lambda. So if we put this in place of kinetic energy, we will write h nu minus h nu prime, and then we will square and rearrange the terms, and then compare the p square c square value here 6, and then if we solve this equation, next equation, so p square c square will be, if we put kinetic energy square means h nu minus h nu prime square plus 2 m naught c square kinetic energy h nu minus h nu prime. And if we rearrange or square these all terms, then we will have this equation number p square c square equal to h nu square plus h nu prime square minus 2 h nu prime plus 2 m naught c square h nu minus h nu prime. This is equation number 11. If we compare the equation number 6, which have also p square c square value like this, and if we compare the right hand side, then many terms will be cancelled out, and finally we will have this kind of equation 2 m naught c square h nu minus h nu prime equal to 2 h nu into h nu prime 1 minus cos pi. But this equation we need to find out in terms of lambda, so we will put nu as c by lambda or nu prime c by lambda prime. So if we put 2 m naught c square, h will be common, so nu minus nu naught can be written as c by lambda minus c by lambda prime equal to 2 h square here, and nu into nu prime can be written as c by lambda into c by lambda prime 1 minus cos pi. And if we take this 1 upon lambda into lambda prime, and we rearrange or take LCM, then a lambda into lambda prime can be cancelled out. We will have m naught c by h equal to this, and finally we have got the lambda prime minus lambda equal to h by m naught c 1 minus cos pi, and this is known as delta lambda or the Compton shift. So this effect is known as the Compton effect, and this shift in the wavelength lambda prime minus lambda is equal to h by m naught c 1 minus cos pi. So this shift is independent of the wavelength of incident radiation or frequency of incident radiation. There is no term of lambda or nu in right hand side. So shift depends only on this angle phi, cos phi, because h is Planck's constant, this is constant, m naught rest mass of electron, c is speed of light, and delta is, if we find this h by m naught c factor constant, this is known as Compton wavelength, which is fixed. If we put the values of Planck's constant and mass of electron, rest mass, and the speed of light, it comes 2.426 into 10 to the power minus 12 meter or 2.426 picometer. And this, from this equation we can see the greatest wavelength change is for the cos phi have value -1, so it will give us 2 times of this. So maximum change in wavelength or greatest wavelength change will be for the phi equal to 180 degree or 2 pi degree, then it will be 2 times of this. And if cos phi equal to 0 degree, then cos 0 means 1, so there will be 0, shift will be 0, lambda prime will be lambda, or for 90 degree delta lambda will be equal to lambda c or Compton wavelength. And using this formula, shift in wavelength, we can find out, we can solve different numerical problems. And one is there, this example, X-rays of wavelength 10 picometer are scattered from a target. Find the wavelength of X-rays scattered through 45 degree. If angle is 45 degree, then we can find out using lambda dash minus lambda equal to h by m naught c 1 minus cos phi, and h by m naught c also written sometimes lambda c, and this value lambda prime will be lambda plus this lambda c 1 minus cos phi, and cos phi is 45, phi is 45 degree. Find the maximum wavelength present in the scattered X-ray. Maximum wavelength means for phi equal to 180 degree, we will find the maximum wavelength. Find the kinetic energy of the recoiled electrons. We can find out, use the relation kinetic energy maximum equal to h nu minus nu naught, or hc 1 minus lambda 1 by lambda minus 1 by lambda prime. These all values are known, and using this the equation we can easily find out the shift in the wavelength, and sometimes the wavelength of the scattered radiation, and sometimes we have to find the wavelength of the incident radiation. So using this formula we can find out easily. Thanks for watching this video, and if you are new to this channel, then please subscribe, and if you have any queries or questions, then please write in the comment box. So thanks again. We will discuss soon the next topic in modern physics. Thank you very much.